Hi, I'm Seung Lee. I'm going to present our paper DRANet, Disentangling Representation and Adaptation Networks for Unsupervised Cross-Domain Adaptation. Our main task is unsupervised domain adaptation. The goal of the task is to learn a classifier that performs well on the unlabeled target data. In the traditional method, they run each encoder for each domain to be mapped into domain invariant space. In this concept, the individual characteristics of each domain can be disregarded. One of the most related tasks is the disentangling representation. This is a learning technique that separates the image representation into several components, such as the domain shared and domain exclusive components, or the content and star components. The method in the blue box is only applicable for the pair datasets, while the other method is applicable both for the paired datasets and the unpaired datasets. One of the approaches linearly divide the feature representations into the content and star components, which results in poor performance in our experiments. Our motivation is that the linear separation concept is not suitable for multiple domains. So, we design a separator network, which is a nonlinear function that disentangles representation nonlinearly. Given the feature vector f, we define the content as SF and the style as f-SF. Nonlinear separation is one of our key ideas. In addition, based on our intuition that different domains may have different distributions of their content and style components, we introduce a domain normalization factor which compensates the interdomain difference. Then we design our network DRANet with these concepts. DRANet consists of an encoder E, a separator S, and a generator G. We denote the source domain as X and the target domain as Y. The encoder extracts the features fx and fy from the input images ix and iy. Then, the separator disentangles the features into the content and the style. We apply the domain normalization factor to extract the content. And we build the domain transport features fx to y and fy to x. Because these features are the domain transport features, we use the domain normalization factors. We define wx to y as wy over wx, then multiply it to the content cx. And we add the star feature to the domain adaptive content feature. The reconstructed images and the domain transferred images are generated from the image features and transport features through the generator. We train our networks using the reconstruction loss, consistency loss, perceptual loss, and adversarial loss. Additionally, we design a content adaptive domain transfer module. Our motivation is that batch-wise star transfer is not suitable for complex datasets which contains multiple objects. Some images like the image in the red box would harm the performance of domain adaptation. This module computes content similarity matrix H-row and adaptive star features S-hat-y. For example, the numbers in the table is the content similarities between two domains, and we can find the adaptive star features by using the similarity matrix. The adaptive star features are applied to build the domain transport features. In the unsupervised domain adaptation experiments, our model outperforms the previous method. Also, our model can synthesize visually pleasing domain transport images. Our network, both with nonlinear separation and the domain normalization factor, shows best performance. Our model trained with content adaptive domain transfer module shows much better results. In this work, we propose a novel representation disentanglement method and design a content adaptive domain transfer module. We outperform previous domain adaptation methods in the classification and semantic segmentation tasks. There are some limitations in our work. First is that the content from our separator does not contain semantic information, and second is that the adaptive star feature of the CADT module still takes a role as just global star. Thank you for listening.